Добрый день, дорогие друзья! Приветствуем вас на фестивале науки. И сегодня мы послушаем с вами лекцию «Антибиотики нового поколения» от лауреата Нобелевской премии по химии, руководителя Центра биомолекулярной структуры при Институте Вейцмана, Израиль, профессора Ады Юнат. Встречайте!
Over to you, Professor Yonat.
I can start. Okay. So good morning. I'm very happy to be with you. And I want to talk to you about next generation antibiotics and also to tell you about my blue tree. So you all know that there is genetic code, which is made of only 4 letters in the DNA. The genetic code in the DNA is coding for the various proteins that we need in the body. And the way that it is translated into proteins is first, there is a copy of it that is made on a very similar molecule called RNA, messenger RNA, which is needed because the information in the DNA is covered by the structure. So RNA can stay as a single helix and it is available. And then it can be translated to proteins by ribosomes. And this happens in every cell. All ribosomes perform their 2 major functions, decoding of the code and peptide bond formation. It means making the proteins in a similar way, actually the same way. They act very fast. They can make 40 bonds with hardly any mistake. And for human beings like me, when I was a student, it took hours to make 1 bond, and they are preparing the proteins according to the needs of the cells where they are. So now that we know how they work, we know that they are made of 2 subunits, which are shown here as a factory with 2 floors. So the top floor is reading the code. Here the code is coming in. And the lower floor is where the protein is being made. The amino acids, which are the components of the proteins, are being brought by trucks, which are also RNA molecules called tRNA. And when here there is a code, every code is 3 letters, 3 bases of the genetic code. When 3 letters that are coding for this amino acid, each amino acid has its 3 letters, then this will come in and be connected to the growing protein, and this happens inside the ribosome in the first floor. When this will be connected, the protein will be longer by 1 amino acid. The carrier, the tRNA, can go out empty. There will be a little energy involved in it, and the genetic code will progress by 1 code, which is 1 codon, which is 3 bases. So actually what you saw here, and I already said it, ribosomes are made of 2 subunits, large and small. The small is the top floor of the factory, is responsible for translation, for decoding, and the lower one makes the bonds. So this looks like this. Here is the small, here is the lower one. The track, which is a tRNA molecule, is being decoded here and gives the amino acid to the growing protein here. So the small subunit is where the decoding happens, and the large where the bonds are being made. So once we got the structures, immediately we understood how the ribosome works. It took 20 years to get the structures, but only a few months until we understood. And we got together with 2 students of the Art Academy in Jerusalem, and we made this little movie, little video, as you want to call it. which explains what I said now, but much more like ribosomes, not just like just a company. And somehow it doesn't want to, oh, here it comes. So the messenger RNA with the code is reaching the small subunit. The two subunits are separated in the cell and comes into its path. And this is monitored by initiation factor. There are in bacteria 3 factors, in human many more. And they made sure that everything is fine. So initiation factor, first of all, reaches the small subunit, binds to it, and now it does its role, making sure that the messenger RNA is in place. Now comes the first tRNA. It's being brought by another initiation factor, number 2 in bacteria. They put it in place when after everything is fine, the factors leave. Here is the tRNA, the track with the amino acid, and the large subunit can reach the small one and make bridges. Now there is a ribosome. This is the active ribosome. You can see it now from the solvent side. On top is the large subunit, below is the small one. And amino acids are being brought by tRNA from the left side with elongation factors. The ribosome helps in, out, 40 times a second. And we took away the large subunit so you can see how the peptide bond is being made here in the small one. And from the large one, we took away, but we left only the tunnel through which the newly born protein will go out. So you can see how the bond is being made and then how they go into the tunnel. Now you see again the whole ribosome. The tunnel is blinking here. More and more amino acids are being brought here according to the code. The protein grows, comes out slowly from the lower part and folds along with chaperone. And when there is a code saying stop, finish, there will be a release factor, this gold thing that comes here, that terminates the production. That's it. Now the ribosome, the tRNAs, the messenger all can go to make a new protein, and the protein that was being made, the blue one, can go and do what it needs to do. That's all, ladies and gentlemen. Isn't it very, very, very elegant? So actually we know the position of each and every atom in the small and in the large subunit. Ribosomes are made of RNA. This is the gray, very many RNA bases, ribosomal RNA. And many ribosomal proteins are shown here in many colors. So just to remind you, the small one is doing the decoding and the large one makes the bonds. So there is a huge number of ribosomes that function in every living cell. Mammalian cells, like liver cells, can contain 4-5 million ribosomes in each cell. Even in bacteria, there are up to 100,000 ribosomes. Owing to the vital role that is played by ribosomes, almost half of the clinical used antibiotics are stopping protein biosynthesis, usually by paralyzing the ribosome. So the natural antibiotics are the weapons that microorganisms from one type is using for interfering with cell life of different species. It means it's the tools for the fights between bacteria to bacteria. So, but some of them are really useful for a clinical use. Those that can distinguish between ribosomes of bacteria and of human. Let's have a look of 4 antibiotics. Look at this one, so small. It was discovered in a country close to yours, in Poland. And look how clever, so small, just doesn't let the code coming in, the messenger RNA. That's it. No code, no translation. The second one is even smaller and it's more useful because of medical reasons. And it occupies the position of the second tRNA. Just sits there. That's it. No way. The third one that you will see in a minute is called erythromycin. It's the first one from the ribosomal antibiotics that went into usage. And it sits in the tunnel, in the beginning of the tunnel, in the top side of it. See, just here, doesn't let proteins go. And the last one is called clindamycin. You will see it in a minute. From the chemical point of view, is the cleverest. It just goes into the bond. You remember the bonds are being made here? Chop, into the bond. Isn't it clever? Very clever. So essentially, all antibiotics, all useful antibiotics that target ribosomes, target them in a blocking sites, functional sites, like the decoding or the bonding or the hinging. These are the motions that you saw, or the tunneling. And I didn't show here, I'm sorry, entrance of the tRNA. Each of them blocks a functional sites. So when the antibiotics came into use, the pharma companies jumped on it and made them better, improved them. They made a whole family called macrolides from erythromycin. This is the example that I show here. And have a look how much chemistry they did to make it less poisonous, faster, more efficient, very clever things, but using the core that the bacteria made. So since antibiotics are targeting functional sites, and since functional sites are very common to all life, also to the patients and to the infectious bacteria, only very small variations are between them, and we are using those that are affected by these variations, and I won't show more about it now because I want to talk about resistance. I'm sure you know that the resistance to antibiotics is one of the most severe problems in modern medicine. Bacteria, the way they become resistant, they either profit from accidental mutations and sort of pick up the good one, or develop specific molecular pathways that cause resistance. And we have no time to discuss each of them, but to remember that there are several ways to acquire resistance. And I'll give you some numbers that show how bad resistance is. In USA, 2 million people fall ill in infectious diseases every year. In Europe, between 2010 and 2014, resistance cost 33,000 deaths each year, although there was 1.6 billion healthcare costs and a lot of productivity uses and losses, and although the consumption of the antibiotics went down in some examples even twice as much as needed, or it was supposed to be needed. So it seems that we will soon revert back to the pre-antibiotic era, during which diseases caused by parasites like simple or severe infections like pneumonia or even wounds were almost untreatable and resulted in frequent deaths. Or we are reaching post-antibiotic era. It doesn't matter, as long as we understand that antibiotics become less useful because of resistance. And consequently, the World Bank estimated that up to 3.8% of the global economy will be lost by 2050 because of resistance. Yet, only a few new antibiotics are in development by the companies. Most large drug companies stopped attempts at creating antibiotics owing to the huge mismatch, a huge difference between social value and the high expense needed for creating new antibiotics. So you can see here two tables. On the left, the one that shows how resistance grew in 3 different bacteria between 1990 and 2002, just 12 years, and see what is the extreme growth of resistance. On the right side, you can see how many antibiotics were made since 1980 to 2018. It means 38 years. Look how very few of them. And it becomes smaller and smaller every year. So let's ask myself, what is my opinion about combating resistance to antibiotics in full? It means stopping resistance. My own opinion is that it's unlikely because bacteria want to live and because bacteria are cleverer than us, at least in terms of survival. Yet, we decided to do some things, whatever we can contribute, modest contribution, toward controlling or maybe combating antibiotic resistance. So our concept for fighting or controlling bacteria's wisdom is identify species-specific, pathogen-specific antibiotics by going to essential structural motifs that are on the ribosome, but not in the active sites, but only at its periphery, at its surface. Since these sites are very far from the active sites, so far, no bacteria has a resistance against it. So our concept is design narrow spectrum that are narrowing the risk of resistance. So for this, we determine the structure of ribosomes from pathogenic bacteria and compare them to the structures of harmless bacteria. And we learned many lessons. I will not tell you all of them. The general one is that all bacterial ribosomes are very similar, but only similar, they are not exact. Lesson 1, 2, and 3, I won't talk about. Lesson 4, this is beyond our expectations. Novel binding sites. This is what I said in the beginning, on the periphery. So you can see here the large subunit, the skeleton of the large subunit from harmless bacteria in gray, non-pathogenic, and a little additions of the pathogenic. It's less than 8% of the total number of residues, but it sits in specific places and has specific sites that they gave us the feeling that we can use them. Like, let's have a look at one of them. We should focus on this one, lower one. You see, the neighborhood of the pathogen and the non-pathogen is very similar, almost the same. But here there is a little piece of the pathogen, and we think that it can be a potential binding site. So we identified many of them. This is what I just showed you, and we identified all those potential binding sites. Actually, we identified 25 new potential binding sites and blocked them one by one. And 16 of them, when we blocked them, they stopped protein biosynthesis, each of them. And these sites are not involved in primary ribosomal activity, not in decoding, not in peptide bond formation, and no pathogen has any genetic code for any genes for modifying them. So at least for now, we are safe with them. This means that so far, no bacteria assigned vital roles for these sites. Nevertheless, they are very important in the cellular aspect, not in single ribosomes, but in the cellular. And for now, these sites can be exploited for the design of advanced degradable antibiotics, hence environmental friendly. So I didn't talk about degradable and environmental, and I will talk about it now. First of all, I want to show you examples of 5 of these binders to the sites. You can see here, and you can see that they have a very nice inactivating values. Second, I want to show you what I mean by selectivity and similarity. So we start with microbiome. The microbiome are the good bacteria, the harmless bacteria that are residing in the flora and are exposed in mammalian organs like guts and ears and lungs and skin. Most are extremely useful, and because they are mainly new bacteria like the disease-causing bacteria, they can be harmed by the antibiotics that are used for the normal diseases. Second, I want to show you that we expect that our new antibiotics will be able to distinguish between bacteria and human or other animals. You can see here in the red and in the blue and in the green, the additional parts of higher animals compared to bacteria. They are mostly on the surface. I will not go one by one and explain, but you see mostly on the surface. So all those antibiotics that go to the surface of the antibiotics and to the places that are under the positions of additional, they are safe for usage. So now, environmental and ecological considerations. So most of the ribosomal antibiotics are extensions of internal pieces, cores like this, that were designed by the bacteria. And those, all of them, are not digestible and not degradable. It means that when we take antibiotics, or we prescribe antibiotics, or animals take it, even in the allowed concentrations, they come out to the sewage. And because they are so small and they are not degradable, the irrigation, the filtering systems cannot see them. Some of them are even toxic. Furthermore, they can penetrate the agriculture irrigation systems and come back to us via the grass or the milk or whatever grew on this lands and increase resistance. So, oops, sorry. So we want to eliminate them, not to use them. Therefore, our suggestion for the new antibiotics for inhibiting biosynthesis are by using degradable compounds, or at least not poisonous, oligopeptides or oligonucleic acid or similar one. And so far, all the 16 that they can be optimized by this type of compounds. So the chemistry is in our hands, and we can control it, and we can make it biodegradable and not poisonous, and similar other considerations that I won't talk about it now. I just want to show another aspect. Until now, we talked about the antibiotics, almost half of them, and anti-ribosomes. Now, I want to talk about cells that develop, all cells, specific methods for preservation under stress. So you can see here, under stress, when there is a big stress, and cells cannot grow, but wants to preserve, and they want to preserve the ribosomes. Maybe once the problem will be, they make dimers. You see here dimers of 2 ribosomes, and each of them is preventing the other one from functioning by blocking the entrance of the other factors or whatever. They just stop it. So this is a way that the cells are preserving the ribosomes. But each type of cell has different ways to make these dimers. You can see here 3 different ribosomes from 3 different bacteria. You see that they look a little different, and when they are together, the 2 of them, I made it here, one on top of the other. You can see that there are many regions that are specific for each of them, and we think that they can also be targets for new antibiotics. So in summary, the new insights obtained from these high-resolution structures of the ribosome from genuine pathogens provide unique chemical tools for suggesting novel sites. I showed this for suggesting how to improve clinical performance. I didn't show, you may believe me if you want, but this was lesson number 2. For better distinction between pathogens and useful bacteria species in the microbiome, I showed it. And for making pathogen-specific antibiotics, this is what I talked about a few minutes ago, a specific antibiotic for each and every pathogen. So we are aware of the problem, economical problem, that companies don't want to make wide-range antibiotics. Of course, they don't want to make pathogen-specific antibiotics. Nevertheless, we expect the pharma companies to consider human aspects, it means our lives, not only profit. And also when they think that many people will die will die young, less of their expensive products will be sold, maybe they will reconsider. So now for almost the whole lecture, our structure-based specific antibiotics are designed to minimize widespread resistance. We are not sure that we can fight resistance, but at least minimize it or delay it. To minimize microbiome destruction, to minimize environmental hazards. Moreover, currently, because we accumulated so much knowledge about ribosomes, currently we are extending our studies towards exploiting the specific motifs and technology for treating human diseases. And there are diseases that are caused by mutations of ribosomes, mainly cancers and anemia. So we are trying now to understand and maybe fight them. Before I finish, I promised you a blue dream, which I didn't promise in the beginning. Let's look at my blue dream. This is life expectancy in the world about 2008 or something, 2012. The highest life expectancy over 80 is in Canada, Australia, New Zealand, North Europe, and Israel. And I don't want to go country by country, but I want to highlight that there are still countries that life expectancy is less than 50 years. All these countries here and here. And my dream is that the whole world becomes blue soon. So for materializing my blue dream, a serious commitment of the pharma companies is essential as soon as possible. And if you know any pharma company that is ready to go into new antibiotics and they are ready to collaborate or to talk to us, I'll be very happy. So before I finish, I want to thank the Weizmann Institute that let me work on what was called my dream and my fantasy for many years, maybe 15. The decision was made by Professor Michael Sela. He's a biologist, immunologist, and everybody says it's because of it. But when he was replaced by Chaim Harari, who is a physicist, high energy physicist, he didn't change it. This is because the advisory committee encouraged them. They didn't think that I can come to the end, but they said a project like this shouldn't be stopped. The head of the committee was Sir John Kendall, that determined the structure of the first proteins, hemoglobin and myoglobin, together with proteins. And Chris Anfinsen from Bethesda, that showed that proteins have to have structure in order to function, both Nobel Prize winners. But I got support also by Dr. Alex Rich, Professor Alex Rich from MIT. Now all of them are not alive. Alex tried to crystallize ribosomes to determine the structure for 10 years and failed. Still, he was supportive, and I thank him very much. It all started in a very extensive collaboration with Max Planck for molecular genetics in Berlin, with their director, that all what he wants is to see the ribosomes, how they work and how they are built, who encouraged us and also played a major role in starting or establishing a group for us in Hamburg at the synchrotron, which we were using for measuring. Unfortunately, he died 10 years before we got the structure, and he was replaced by Franceschi and then by Fucini. So I had two research groups, and I want to thank for their devotion and determinations in good and in bad times for many years. This is the group in Hamburg. It always had angels because they say that only angels can work on ribosomes, the technicians. And they also came to Israel to look for bacteria in the Dead Sea, a better one than the one that we were using. Actually, this was our beginning. And I want to also show you the group in Israel. These are people that have been there during the last 5 years, and those that are still there are shown in these little green stars. I want to highlight Anat, Dr. Anat Bashan. She's actually the head of the group. She's running it. She has been there for many years. She was even a student with us. And I want to highlight Tamar, who came to us 18 years ago for 10 weeks. She's still around. At the day that I took this picture, she had her birthday. And she baked a cake. Can you see the cake? Maybe not clear, so I will show you. This is a cake, and it shows that in my group, ribosomes are considered sweet. I also want to thank my family, my mother, my sister. I show here only my daughter and my granddaughter, but they were all very, very supportive, despite my frequent disappearances. Here is a speech that my granddaughter gave when I got a prize in Paris. And she said, as you know, she, it means me, is a very busy scientist, but she always finds time for me. And she even gave me a prize. This is not her prize. This is the Nobel Prize. But for me, her prize is at least as important. The grandma of the year is Ada Yonat. And when I asked her which year, she said, which year? You have to reprove yourself every year. Otherwise, I take it off the wall. And you can see it's still on the wall. Ribosomes became popular in Israel. This is a carnival. He is me, and she is the ribosome. You see, they are dancing here. A protein comes out of her. Even young children became ribosomes. And Michel Kishka, our artist, the Israeli artist and writer, drew this head full of ribosomes. And if you look closely, large subunit, small subunit, all symmetrical. And he thinks that new antibiotics should be here, and of course here and here too. Thank you.
Thank you, Ada. Благодарим нашего спикера.
Thank you very much, Ada. Can you hear the translation?
Has some questions. And first of all, dear professor, thank you for your interesting lecture. And there is a theory about last chance antibiotics. How much do you think it has to be?
Last chance? I never can say last. In science, somebody can come with an idea that I didn't think about. I only can tell you about our idea, and maybe even us will have more ideas. And last, there is no last.
Thank you. And one more question. Not many people understand how antibiotics work and how they function inside our organisms. How often are you asked absurd questions, and how often do you suppress myths about antibiotics?
How often what?
Once again, please.
How often?
No. How often are you asked?
Yeah, I just
how
showed how
often
they
do
work.
you ask?
I showed how they work. At least I showed 4 of them.
Okay. And do you think that popularization of science will contribute to the fact that such that such myths will appear less and less, and people will more correctly monitor their health, and as a result will be healthier.
I don't know what is popularization of science, but I know that if people are interested in science, it's better. And if people can contribute, it's even better. And if people are not afraid of science, it's of course better.
Thank you. Thank you. One more question. Is the significance of science, especially in our time, enormous? And how do you feel about this interest? And for example, now you are performing at the largest science festival in Russia. How do you feel?
Feel great that people want to listen something about science, and that's already good. And thank you for inviting me.
Thank you for your lecture and for your magnificent presentation. Thank
Sorry
you.
that I don't understand Russian, so I couldn't understand everything, but whatever I understood was nice.
Thank you. And
Спасибо.
can you... Thank you. Спасибо вам. Can you give some words for our viewers, listeners, some words about our festival, some please words?
Some what? Which type of words?
Can you please?
I can say,
Can you hear me?
thank you for listening and thank you for being interested in scientific topics and scientific progress. Good luck to all of you.
Thank you. А мы благодарим наших зрителей за посещение.
We would like to thank our viewers for being here at the Moscow Science Festival. So you just listened to the lecture about new generation of antibiotics, and with us we had Ada Yonath, Nobel Prize laureate. Thank you very much, and goodbye.
В жизни всегда есть место открытиям. Откройте Web Gallery.
Встречай Сбер, твой банк. А еще Сбер – это целая вселенная. с универсальным доступом. Легко и просто. Выгодная подписка. На все сразу. Салют. Умный ассистент поможет выбрать фильм на вечер, поговорить о жизни.
А ты хороша.
Спасибо за комплимент, Андрей.
А еще доставим, накормим, довезем,
Что-то еще?
отправим, сориентируем, поможем бизнесу взлететь. С нами 100 миллионов клиентов. Такое кино, такие новости, такой звук. Сбер. Больше, чем банк. Сбер для жизни.
Что снимать в TikTok Live? Да что угодно. Сними, как тебя разбудило солнце, или как ты разбудил соседей. Сними свой завтрак, или тех, кто не дает тебе позавтракать. Покажи привычный вид из окна, или вид, к которому не можешь привыкнуть. Увлекаешься чем-то? Покажи это. Просто снимай, а зрители найдутся. Снимай, если на работе произошло что-то интересное. Или твоя работа — это и есть что-то интересное. Покажи, как пропадаешь дома. Покажи, куда едешь. Или почему пришлось остановиться. Покажи что-то новое. Покажи неизменную классику. Покажи тренировки. И покажи результат. Покажи семью. Покажи друзей. Ведь твоя реальная жизнь — это и есть самый невероятный контент. Покажи, чем ты живешь. Посмотри, чем я живу. TikTok Live.
Границы Вселенной, скорость мысли, невидимые миры, абсолютный ноль. Все это не просто слова. Это телеканал «Наука». Нам есть чем вас удивить.